All right, everybody, welcome to Math with Grace. Today we're going to be working through Pre-Calculus or Math 12, Unit 1, Section 2. Section 2 begins on page 28 and it's titled Algebra of Functions. And it's got a lot of subtitles. I'm not going to read all of that stuff, but it says mathematicians over the years have developed a language of notation. So we're going to be talking about notation and how it allows people to communicate effectively when talking about math. At the bottom of page 28, we see function notation, okay? And function notation is basically replacing the y in an equation with an f of x, okay? F parentheses x is read f of x, or f is a function of x, okay? In certain situations, a letter other than x will be used, but in general, we use x to represent the domain values, okay? The variable inside the parentheses represents each element of the domain, which remember is the independent variable. The domain can be any number except those that would make the function undefined. The entire symbol of f of x, see this example right here, f of x equals 3x plus 4, that entire thing represents each element of the range, the y value, the independent value, the dependent value. It says here, notice that f of x replaces the y value that you are familiar with. So y is equal to f of x. All right, continuing on to the top of page 29. Let's evaluate some of these functions. So beginning with y equals 2x minus 7. To write that in function notation, we would simply replace the y with an f of x. So we have f of x equals 2x minus 7. We could then generate some ordered pairs by choosing some x values and then solving by substituting the x value for the x and solving for the f of x or the y value. Okay. Then we could write these as ordered pairs. They didn't in this case, but you could. But how we represent that, since we are replacing the x with a value, we write f of negative 2 equals negative 11. That basically is stating that our ordered pair is negative 2 comma 11. Same here, f of 1 equals negative 5. Our ordered pair is 1 comma negative 5. Okay? In the next example, we have f of x equals 3x plus 4, and they want you to solve for f of 2. To solve that, we simply substitute the 2 for the x, and then do the mathematics to solve. Okay, so the ordered pair, here they have written it, as is when x is 2, y is 10. Now, for example 2 here that I have marked, it says, given that, I'm going to scooch up a little bit, given that f of x equals x squared, we may form a solution set. Okay, just kind of the exact same thing they did up there. They chose values for the x, and then they solved that to get the y value, and then they set up their ordered pair solutions. Okay, so we just substitute it in like normal. Now, example 3 here at the top of page 29 says that the area of a circle is found by the formula a equals pi r squared. The area, a, is a function of the square of the radius r, which means that the value r is the domain. It's the independent variable, okay? And it's the values of a are the range values, and they're dependent on the radius, right? The radius determines what the area is. So the radius is independent, while the area is dependent, okay? So they can set up an a of r. Same as the f of x, right? They're just using different letters. So it's an a of r equals pi r squared. Again, they choose some radiuses and solve. They've made a little chart, but your chart can also be written as ordered pair numbers, okay? So one other way you can solve these is for a non-constant, okay? And what that means is if we have the function f of x equals x squared plus 2x plus 1, we can solve that for f of a. And basically the a is then substituted for the x's. F of r, same thing. F of a plus 1, now we're putting the a plus 1 in where our x values are and then completing the equation. Okay, multiplying out, adding our like terms, simplifying. In each case, when we are given a function and then they give us a value to put in for our x, we are substituting that in and then simplifying where possible. Okay, let's turn the page and do some of these problems together. So I'm on page 30 and we're going to take a look at problem 2.3. It says solve f of x for the given domain. F of x is equal to x squared plus 3x minus 2, and they want us to solve for f of 1. Well, for f of 1, we are simply going to substitute a 1 for every place that there's an x. So that tells me that 1 squared plus 3 times 1 minus 2 is going to be our function. 1 squared is 1, 3 times 1 is 3, and our minus 2 is not affected by any of it. So 1 plus 3 is 4, minus 2 is 2. Our answer is A. All right, let's take a look at number 4. Solve f of x for the given domain. F of x is equal to x squared plus 3x minus 2. And they want us to solve for f of 3. So just like in the previous problem, we're going to substitute the 3 in where we have an x. So we end up with 3 squared, not to the third power, plus 3 times 3 minus 2. 3 squared is 9. 3 times 3 is 9. And minus 2. So we have 18 minus 2, or 16. Our answer is B. Solve f of x for the given domain. We're on number 5. F of x is equal to x squared plus 3x minus 2. Solving for f of negative 1. All right, well, f of negative 1, and the book is using a capital F. I just have a tendency to use a lowercase f. When I went to school, they were all lowercase f's, so, or other letters too, but they were all lowercase, so that's just what I'm used to. But feel free to use capital F, it's fine. So I have negative 1, the quantity squared, plus 3 times a negative 1 minus 2. All right, negative 1 squared is a positive 1. 3 times the negative 1 is a negative 3 minus 2. So 1 minus 3 is negative 2 minus 2 is equal to negative 4. So A is our answer. Okay? Let's take a look at problem number 7. 7 tells us to solve f of x for the given domain. Include all of your work in your final answer. Okay, no multiple choice on this one. And they want us to solve f of x equals x squared plus 2x. And they want us to solve for f of x squared. So f of x squared is going to be x squared squared, right? Because this is a squared term, and we're substituting the x for x squared, or the x squared for the x. Plus 2. Now remember, when we have a power to the power, okay, we multiply our exponents. So this is going to be x to the 4th plus 2. Okay, and that is all my work in my final answer. I suppose we can write it on this line. X to the 4th plus 2. All right, let's do another one of these up here, problem number 8. For problem number 8, it says solve f of x for the given domain. Include all your work in your final answer. Okay, f of x is equal to x squared plus 3x minus 2, and they want you to solve for f of a. Well, we're simply going to substitute the a for our x's. So we're going to have a squared plus 3a minus 2. So a squared plus 3a minus 2. There's not a lot of work to be shown, but that is the substitution. Let's take a look at number 10 next. Solve g of x for the given domain, include your work. Okay, so we have g of x is equal to 3x squared minus 2x minus 1, and they want us to solve for g of a plus b. All right, so this one was a little bit more complicated. So we have g of a plus b is equal to 3. Now our x, we're substituting a plus b, but that quantity is squared, minus 2 times a plus b minus 1. Okay. Now, we have to square before we can do distribution of our 3. So we are squaring this a plus b. Now, it is a quantity squared, right? Is a binomial squared. So what is our trick for binomials squared? That's right. It's going to be a square double square. So we're going to square the first term. We're going to multiply a and b together and then double it. So plus 2ab. And then square the last term, b squared. This we can go ahead and distribute. So minus 2a minus 2b minus 1. So now we need to distribute our 3. So we're going to end up with 3a squared plus 6ab plus 3b squared minus 2a minus 2b minus 1. We need to write this in the correct order to be mathematically consistent. So we have 3a squared, then our minus 2a is going to come next. There's nothing here that can be combined. There are no like terms, so we're really just writing this in the correct alphabetical order. 6ab, and then minus 2b plus 3b squared minus 1. I'm not going to rewrite it on that line, but that's what our answer would look like. Okay, so just take your time. You're substituting in. I can't remember if there's more problems. There are a couple more problems on the next page, but that's all we're going to do together today. But take your time. You're substituting in. Solve, combine like terms if possible. There's nothing in this particular problem that was combinable, so that just becomes our answer. Go ahead and finish this section or this part of section 2 and then meet me for the next part. All right, the next part of section 2 begins on page 33 and it's titled Algebra of Functions, Arithmetic. Now here it says equal functions have the same domain and each value within the domain generates equal range values. So when we're talking about equal functions, they are literally the exact same thing. So two functions are said to be equal if the two functions have the same domain, and for each value in the domain set, the function values, or the range, are equal respectively. So for these to be equal functions, they literally have to be equal. Now, they try to throw us off here by writing them in a different order, but they're the exact same thing. Function f is exactly the same as function g, just their numbers, their ordered pairs are not written in the same order, which is fine. They still both have a 3, 4, they both have a 4, 5, they both have a 2, 3. They are equal functions. Okay, let's turn the page. At the top of page 34, we start talking about adding and subtracting functions. And the addition rule is here. Two functions may be added together only for common domain elements. What that means is this is kind of a specific answer to these ordered pairs. So we'll take a look at that in a second. Symbolically, f of x plus g of x is written like this. F plus g of x. Okay? And here is example 1. For example 1, we are given our f of x and our g of x, ordered pairs. When we add them, we can only add them for common domain elements. So they both have a 2 domain, right? They both have an 8 domain, and they both have a -2 domain. So those are the things that we can add. Their common domains are 2, 8, -2. Therefore, we take the range of the 2, so here's our domain of 2, and then we take the range, the 3 and the 5, and that's what we can add together. We go to the domain of 8s, and they have a range of 1 and 6. That's what can be added together. We go to the domain of -2. They have a range of 3 and 3, and that's what can be added together. So once we add those together, we get this. but that tells us that our range is 876, 876. Okay? So that's how you do it with ordered pairs. That's how you can add with ordered pairs or subtract or anything else. They don't really go into it a super bunch. I know they talk about it in multiplication a little bit more, but this is not really a common way we do things. But example 2 here at the top of page 34 is. So f of x is equal to 2x plus 3. G of x is equal to x minus 7. So when we are adding f plus g of x, we are going to be adding 2x plus 3 plus x minus 7. We combine our like terms and then we get our answer. Very simple. Now, we can also do an evaluation after that. So if they want f plus g of 1, you can solve for my f plus g and then substitute the 1 in and get your answer, which would be exactly the same as if you put a 1 in to the f of x and then put a 1 into the g of x and then simply added those two answers together. You would get the same thing. So either way, it works out the same. Now, subtraction, as we're starting to talk about here on middle of whatever, second column of page 34, works the same as addition. So f minus g of x, or f of x minus g of x, either way, you can write the notation, okay? And you can see here that they don't go into the ordered pairs, but they do have our expressions here to be subtracted. Now, notice that when you subtract a function, the negative sign applies to the entire function. This negative has to be distributed. Do not forget that, okay? That is Algebra 1 business. Do not forget to distribute your negative. That's what they're saying right here, okay? All right, top of page 35, multiplication. F of x times g of x. The function values may be multiplied only for those values the domains are equal. They're talking about here, right? Again, same ones that we used in this example over here. So we have the 2, the 8, the negative 2. So only my 3, 5 can be multiplied. My 1 and 6 can be multiplied, and my 3 times 3 can be multiplied. Okay, and we come up with this new set of ordered pairs. When we're talking about expressions, okay, with our functions, then we literally have to multiply the two expressions together. They tell you here to use the FOIL method, combine your like terms, and simplify. All right, that's for the multiplication. And then, of course, there is division as well. Division, f of x divided by g of x, follows the same procedure as multiplication, except in this case, my g of x cannot be equal, cannot equal 0. The denominator must never, ever be 0, okay? So again, they've got the exact same set of ordered numbers, ordered pairs, and they just divide instead. It's pretty straightforward. Setting up our division problem here, okay, is very straightforward too, because we can't reduce anything, but the difference is with the division is we have to note our excluded value, okay? In this case, x cannot equal 5 over 2. And you might be saying, well, how do you know? Well, remember, when we have a expression in our denominator, we set that equal to 0, and then we solve for x. So we would add 5 to both sides. 2x is equal to 5. Divide both sides by 2. X, in this case, cannot equal 5 over 2, because if it does, then this denominator will be 0. So we need to make sure we note that in our answer. Okay, we have to list our excluded values. All right? Okay, that's it for this part of the section. Let's work on some of these problems together. I'm going to start over here on page 36. We're going to take a look at number 16. Given this function f and this function g, they want to know what is f minus g of 6. Now, Let's take a look at where they actually match up. For my domain of f, I have 0, 2, 4, 6. For my domain of g, I have 2. Well, I know I had a 2 over there. 4, 5, 6, 7. Okay? So they match up in 3 spots. 2, 4, 6. But they're asking for f minus g of 6. Okay? Well, my 6 is here. So it would be f minus g of 6 is going to be 6, comma, 8 minus 9. Okay, that's the ordered pair. Remember, the domain stays the same. We're only adding or subtracting, in this case subtracting, the ranges. And this 6 in the first function they gave us is 8. And this range in the second function they gave us is 9. So it would be 8 minus 9. So that tells me that f minus g of 6 is b, negative 1. Because that's what the range would be. Right? 8 minus 9 is negative 1. Okay? Looking at number 17, f of x equals 2x and g of x equals 3x minus 5, f plus g of x. Okay? So for f plus g of x is going to be our f, x plus 2, plus our g, which is 3x plus 5. Let's combine our like terms, right? We got this and this. So we have 4x plus 7. So B is our answer, 4x plus 7. Let's take a look at number 18. F minus g of x. Okay, now these are the exact same f and g, but let's go ahead and set them up anyway. So we have f minus g of x is equal to x plus 2, that's my f, minus my g, which is 3x plus 5. Now remember, we have to make sure we distribute this negative through. So it's x plus 2 minus 3x minus 5. Now we can combine our like terms, and we are going to get negative 2x minus 3. Okay, negative 2x minus 3. Now, they're kind of, I don't know what's up with this, again, with this multiple choice, but that's fine. That's how they decided to set up their problems, okay? Let's take a look at one more here, number 19. Well, I mean, we're going to do more than one, but for now, and it says f of x is equal to x plus 2, and h of x is equal to 1 over x minus 1. They want you to solve for 2 f of x minus h of x. So we have 2 times x plus 2 minus 1 over x minus 1. That's what is happening right here. Okay? So we have 2x plus 4 minus 1 over x minus 1. Now, how do we get rid of a fraction in an equation like this? Well, we have to multiply every single term by the denominator, right? That's just what it is. So 2x times x minus 1 plus 4 times x minus 1. And then in this case, the x minus 1's cancel, so it's just minus 1. I'm going to run out of space here. 2x squared minus 2x plus 4x minus 4 plus, or minus 1. Minus 4, minus 1. Okay, remember I distributed all of these through. So now let's combine our like terms. This are like terms, and these are like terms. Okay, I'm going to write it over here because it's going to be our final answer. 2x squared, negative 2x plus 4x is 2x, and negative 4 minus 1 is negative 5. Okay, so a lot of old algebra is coming into play here. We need to make sure we are simplifying our problems all the way. Looking at number 20, we have f is this ordered pair, g are these ordered pairs. They want us to multiply f times g of 2. So here's a 2, and here's my 2. That tells me for my 2, I'm multiplying 4 times 5. Remember, that's my range here and my range here. Those are the only things that we can multiply. So 4 times 5 is 20. So B is our answer. Okay? Let's take a look at one more of those before we go on to the next page. So given f is this set of ordered pairs and g is this set of ordered pairs, complete the ordered pair for the function f of x divided by g of x at 4. Well, here's my 4, and here's my 4. So at my 4, I'm going to have 6 divided by 7, right? This one's first, so it goes on in the numerator. This one is second, it goes in the denominator. Well, plus, that's what it says here, f of x, g of x, right? So 6 divided by 7, A is our answer for that one. All right? Good job. Let's keep going. Let's take a look over here on page 37 at number 24. Given f of x equals x plus 2, they want you to find f of x squared. Okay? So it's going to be x plus 2 squared. And we just did one of these a little bit ago. Remember, when we have a binomial squared, it is square double square. So you square the first term, you multiply the 2 together, so 2x, and then you double it, and then you square the last term. I guess I could have wrote that right on the line. X squared plus 4x plus 4. Okay, square double square. Don't forget the square double square. All right, go ahead and finish the rest of these problems on your own and meet me back here for the next part of section 2. The next part of section 2 begins on page 39. It's titled Algebra of Functions Composition. It says composition of functions is substituting the range values of one given function for the domain values of another function in order to find range values for the composite function. These are a lot of words. It is not as complicated as that sounds. In order to do this, the range values of the first function must be contained in the domain of the second function. Again, it is not as complicated as it sounds. We will get into what all that means here in a moment. So it says, what is a function composition? It says to combine two functions by composition. 1, find the range values of the first function. Okay, so basically you solve the first function for y, or the answers, right? And then match them with the domain values in the second function, which either means when they're talking about ordered pairs, you find the right domain value. If they're talking about two expressions, you're just simply sticking that number into the other expression, okay? Numbers that are paired with the domain values of the second function become the range value of the composite function. Again, this is more leaning towards the ordered pair numbers. Remember that the domain of the composite function will be the same as the domain of the first function. So 2 or more functions may be combined this way. And here's what they look like. Okay, this is how you notate it. Remember, this whole section was about notation. F composite, composed of, the composition of G of X. Okay, it says, it's read, this one's kind of a tongue twister. The F composed of G, or the composition of F and G. It says another form of writing this, which is what I am used to and will be using, is f of g of x. Okay, and it's read f of g of x. This is what I will be using. This is a little bit tongue twistery, and I don't want to get this confused with multiplication, right? So f of g of x, I will be writing it like this. So before composition, we must determine the range of g. It makes sure it's a member of the domain of f. So let's turn the page. Example 1 here at the top of page 40 is expressed in ordered pair numbers, right? We have our f and our g set functions, okay? So from the rules, here's what we need to do. The range of g is 1, 9, 8, 9, okay? Remember the range being the y values. We need to make sure that those numbers are contained in the domain of f. So we have a 1, we have an 8, and we have a 9. So yes, they are contained. They are part of the domain of f. So now we can move forward with actually how to solve this. The range values of f are 2, 6, 7, 6. Okay, the y value. this becomes the range of the composite function. So the first part, when we're talking about f of g of x, the first one, the f, we are taking the range values, the y value. And we're going to combine those with our g of x, but we're going to use the domain of g of x. So we have 5, 2, 6, 6, 4, 7, 3, 6. Okay? So the x value of g, the y value of f is what makes up each of these points. Okay? That's when we're talking about ordered pair numbers. Example 2 here on page 40 is f of x equals x plus 6 and g of x equals 5x. Again, the range of g of x is 5x, and we use that as the domain of f. The range of f is now f of 5x, or 5x plus 6. This is the same as the range of the composite function, and the domain of the composite function is x, which is the same as the domain of g. So f of g of x, okay, we're taking 5x because that's what g is, and you're just substituting that into the f of x. So we end up with 5x plus 6. It's very similar to what we did earlier in the last part of this section, okay? These are much simpler. I mean, this isn't complicated, but I feel like these are a little bit more straightforward. Let's take a look at example 3, top of page 40, second column. H of x is equal to x squared plus 3. J of x is equal to x plus 1. To find h of j of x, think of it like this. H of j of x is h of x plus 1, right? That is j of x. So everywhere there's an x in the h, you're going to put it x plus 1. And that's what they do here, and they solve. You have to FOIL this out or use your square double square, right? Combine your like terms and solve. Then they did j of h of x, right? And so instead of putting the j into the h, they put h into the j, and it looks like this, and it substitutes down to here. And then it says, notice that h of j of x is not equal to j of h of x, right? Here's our two answers. And I wouldn't have expected them to be equal. Okay, even though they're made of the same parts, we put them in different order. So I wouldn't have expected them to be equal. Now, that being said, we're going to do some of those problems in a moment. We've got to cover these 3 unique functions real quick. The first one is I of x equals x. It's called the identity function. This graph of the identity function is a straight line where y equals x, passes through the origin, and has a slope of 1. It bisects quadrant 1 and 3, right? 1, 2, 3, 4. The next one at the top of page 41 is the function c of x equals n. This is called a constant function, n being a constant, okay? In the constant function, each domain value has the same range value. As a result, the graph of this function is a horizontal line. The y-coordinate is constant while the x-coordinate changes. Its graph is the line y equals n. And this is what it would look like if it was c of x equals 2. The function zx equals 0 is called the zero function. The zero function is a constant function whose range values are equal to 0. And this graph is the x-axis. Okay? So those are 3 unique types that they just want to cover before we go on to do our problems together. And we're going to start our work that we're doing together here at the bottom of page 41 with problem number 34. F of x equals 3x plus 2 and g of x equals x plus 5. They want us to find g of f of x. So for g of f of x, I don't use brackets. I just like to use the parentheses. If you want to use the brackets, go right ahead. It is representing the same thing. Okay, so for my g of x, which is on the outside, right, I have an x. So instead of that x, I need to substitute the f of x. So it's going to be 3x plus 2 plus 5, right? This x needs to be substituted, and what's being substituted is this. Okay? And then the plus 5 goes at the end. Combining our like terms, we get 3x plus 7. So A is the correct answer. Okay? Let's turn the page. Let's take a look at 35. F of x equals x squared plus 6, and g of x equals 2x minus 1. G of f of x. So again, this is going to be substituted into here. Okay? So for g of f of x, it is going to equal 2 times x, but our x is x squared plus 6 minus 1. Okay, distributing my 2 is going to give me 2x squared plus 12 minus 1, or 2x squared plus 11. So B is our answer. Let's take a look at one more like this. Let's do number 37. H of x is equal to 1 over x squared, or 1 over x plus 2, and k of x is equal to 3x minus 4. They want us to find h of k of x. So again, this time we're going the other way, but this is going to be substituted into there, right? So for h of k of x, all right, we have 1 over x, but my x is 3x minus 4, plus 2. So this is going to be 1 over 3x minus 2, okay, which is C, letter C. All right, so substitution is what we're doing here. Let's take a look at number 38. Complete the missing portion of the equation. F of x is 1 over x, g of x is 1 over 2x plus 4, g of f of x, f of g of x is going to equal 4x squared what? Well, let's see. F of g of x tells me that the g of x is going into this x right here. So I'm going to have 1 over x, or 1 over 2x plus 4. Now, we can't divide a fraction by a fraction, right? So we're going to flip-flop multiply. So we get 1 over 1 times 2x plus 4 over 1, right? We have to multiply by the reciprocal. So I just had to check the answer key because I was like, what the heck? And the book has this as being an x squared, 1 over x squared. The answer key does. Obviously not my book doesn't have it like that. Because if we solve the way we have solved it properly, it would be 2x plus 4, right? It's just the answer. But obviously they're looking for something more, and that would have to be because the actual book wants us to be squared, 1 over x squared. So starting over, we have 1 over 2x plus 4, the quantity squared, okay? So that's going to be 1 over 1 squared, which is 1. And then we have 2x plus 4 squared. So we square the first term, 4x squared. Multiply these two together, which is 8x, and then double it. And then square the second term. Okay, so that gets us what they want. It's just, there's a typo. So that's supposed to be 1 over x squared. All right, then we would flip-flop multiply, or take 1 over 1 times 4x plus 16x plus 16 over 1, which is 4x squared plus 16x plus 16. Okay, so plus 16x plus 16 is A. All right, so the book's got a little typo. Maybe your book has 1 over x squared. I don't know, but mine did not. So because I took up extra space, let's hop down here to number 40. We have f of x equals x squared. G of x is x plus 6. H of x is 7. And they want us to find g of f of h of x. Okay? So h is going into the f, which is then going into the g. All right, you think of it that way. Bung, bung, bing, right? So let's write it out. G of f of h of x. A lot of parentheses, but that's a lot of brackets and braces and twisty bits anyway. So we have, that is going to be equal to x is the first part of g, right? But that x is an x squared. But that x squared is actually a 7 squared plus 6, because that's all that's left over here. Okay, so did you see how I did that? The first part of the g is the x. The x is actually an x squared. The x squared is actually a 7 squared. So 7 squared plus 6, 49 plus 6 gives me 55 as my answer. Okay, so that's how you do more than 2, right? Multiple. Let's do one more of these triple ones. F of x equals x squared. G of x is x plus 6. H of x is 7, so the same, except we're going in a different order, right? So they want h of g of f of x. So that would say nothing, because my h is where I'm starting, is on the outside, right? But there is no x here. So the answer is just 7. The answer is going to be 7. No matter how many of these we try to put in, there's no variable in my h of x to substitute anything in. So that's kind of a trick question they tried to get you. Can't get us. All right. One more problem together. Page 43, number 43. F of x equals x squared. G of x is x plus 1. Find g of f of negative 2. Well, to find g of f of negative 2, first we have to find g of f, okay? And g of f tells me that this is going to go into here, right? So g of f of x is going to equal x, which is actually an x squared, plus 1. Okay, now we can substitute in a negative 2. So g of f of negative 2 is going to equal negative 2, the quantity squared, plus 1. Or 4 plus 1, which is 5. Okay? All right, great job. Go ahead and finish whatever we didn't cover in this part, and then we'll move on to the next part of this section. All right, the final part of this section begins on page 44, and it's titled Algebra of Functions, Inverse. Okay? If f of x is a given function, then we denote f to the negative 1 of x as the inverse of f of x. So I don't ever call it to the negative 1. I just call it the inverse of f of x. The symbol, the little negative 1, is not an exponent. Okay, so be careful not to confuse the function's inverse, or f to the negative 1 of x, with the function's reciprocal, which would be 1 over f of x. The inverse of a function is found by interchanging its range and its domain. The inverse of a function is not always a function and should be checked by the definition of a function. Okay, finding the inverse. In any form, the inverse of a function is determined by interchanging the x and y values. Here's example 1. G of x is these ordered pairs. All we simply do is swap the x and the y. So instead of 2, 3, it's 3, 2. Instead of 4, 6, it's 6, 4. 0, 10 becomes 10, 0. 1, 5 becomes 5, 1. This is the inverse of g. Okay, g of x. For example 2, to determine the inverse of this function where we have, an expression, I keep forgetting the word. We swap our x and our y. So we have y equals 2x plus 5 is the same thing as what's written here. But now we switch our x and our y, and then we solve for y. So the inverse of f of x is going to be x minus 5 over 2. That's what happens when we solve once we flipped our x and our y. Okay, so finding the inverse of these simple equations is pretty simple, but it can get complicated. Let's take a look at the top of page 45. Up here it says we can combine composition of functions with finding the inverse of a function as well. For example, if you are given the functions f of x equals 3x plus 2 and g of x equals negative 1/2 x, And then you're asked to evaluate the composition of f of g of x, right? So this is f of g of x, same thing. They solved for that. Now, once you've completed the composition, then you can solve for the inverse of the composition, the same way we did right here in example 2, right? They've put their x and the y in this time, and then they've traded them out, switched them. Now the x is here and the y is here, then you have to solve for y, which gets a little messy, but it's not anything that we can't handle. So the inverse of the composition of f of g of x is this number, this here, okay? This expression. All right, so now, once you've done all that, you have to verify the inverse is an actual function. Now, it says here that sometimes the two functions are inverses of each other, just naturally or by design. If f and g are inverses of each other, they basically undo each other to the point where f of g of x is x and g of f of x is x, and therefore they are inverses. That is the clue. If you take the composition of in both orders, right? Like they mentioned on one of the other examples, oh, they're not the same. And I said, why would they be, right? But sometimes they can be. And when they are, it's because these original functions are inverses of each other. So let's just take a look at the example and see what that actually looks like, okay? So it says, in the previous example, we found that f of x it being 2x plus 5 and g of x being negative 1/2, or the inverse of that was that g of x is negative 1/2 minus 5 over 2. That was in which problem? Maybe on a different page. Anyway, we took this function and we found its inverse, and that was that, okay? So verifying that these are inverses, we have to check the composite. So first they take f of g of x, and they solve and they get x. Then they take g of f of x, remember these two pieces, and they solve and they get x. So because they are both equal to x, f and g, the functions that we have written here, are inverses of each other. So that is a way to determine if they are true. So let's take a look at example number 2 now. Verify that f of x equals negative 3 over 2x plus 2, and g of x equals 2 over 3, negative 2 over 3x plus 4 over 3. They verify that they are inverses of each other, which is what we did over here, right? So, right, here's this one. Here's this one. We already did it technically, but that's what they want us to do. To do that, we have to do the composite. F of g of x, and then they solved it to x. G of f of x, and they solved it to x. To verify that they are inverses, right? They said determine the inverse, verify that those are actually inverses. It's kind of like checking your work, all right? Okay, let's turn the page and do some of these together. Taking a look at problem number 52 on page 46, it says, what is the inverse of f of x equals 3x plus 6, and is it a function? So first thing, we're going to write y equals 3x plus 6, and then we're going to switch our x and our y. So x is now equal to 3y plus 6, and then we solve for y, okay? So subtracting a 6 from both sides, we get x minus 6 is equal to 3y. Dividing every term by 3 tells me that y is equal to 1/3 x minus 2. Okay? Y is equal to 1/3 x minus 2. Now, they didn't actually divide. It's right here, right? This is a function because it's a line like everything else. This is our answer, B. They didn't divide it out. They didn't simplify it, in my opinion, enough, but that's okay. Answer is B, all right? If you wrote this and didn't circle a thing over here, I'd be totally fine with that, all right? So 253. Let's take a look at that. What is the inverse of f of x equals x squared plus 5? And is it a function? All right, so we're going to write y equals x squared plus 5. Then we're going to switch our x and our y. So x is going to equal y squared plus 5. Subtracting 5 from both sides, we get x minus 5 is equal to y squared. How do we undo a square? Well, we take the square root, right? So y is going to be equal to, plus or minus, technically, right? The square root of x minus 5. Now, is this a function? The answer is no, okay? And so that would be C is our answer. No, it is not a function. The square root makes it, messes it up. It creates an unfunctionable function. All right. Let's take a look at the top of page 47. What is the inverse of g of x equals 1 over x minus 1? And is it a function? All right, well, y is equal to 1 over x minus 1. Let's switch our x and y. So now x is equal to 1 over y minus 1. Okay. How do I get my y out of the denominator? Well, I'm going to multiply every term by y minus 1. So I'm going to end up, and I'm going to do it over here, with x times y minus 1 equals 1, right? Because these cancel, and that's gone. So then I have xy minus x equals 1. Subtract x from both sides. So x is going to equal, or sorry, add x to both sides. X plus 1. Xy is equal to x plus 1. Y wants to be by itself, so we're dividing by x. So y is equal to x plus 1 over x. I don't know that they want us to reduce it any more than that, because it would be, these would cancel, right? It would be, see, this is, if you're going to reduce it, then reduce it every time, right? That's what it would be. So these become a 1. So y is equal to 1 over x plus 1, 1 over x plus 1. And is that a function? Well, yes, because it's our only option, honestly. But this is a function because this is always going to be larger. It will still be positive. I mean, it can be negative too, so that's fine, but these will always be real numbers. Fractions perhaps, but yes, it is a function. Okay? I don't like this. Like, if you're going to do this here, then you should have done that over here for this problem too. But I didn't make these multiple choice, so you got to work with what you're given, I guess. All right, number 55. Gx equals 2x squared and hx equals the square root of x squared plus 1. What is g of h inverse, and is it a function? Okay, so we have to find g of h of x and then do the inverse, okay? So g of h of x tells me this is going into here, okay? So g of h of x is going to equal 2 times a quantity squared, and that quantity squared is the square root of x squared plus 1. Now, what happens when we square a square root? It cancels itself out, right? So I have 2 times x squared plus 1, or 2x squared plus 2. Now, this is just g of h of x. Now they want us to find the inverse. So let's make this a y, and then let's switch it, right? So x is going to equal 2y squared plus 2. Now I need to solve for y. I'm going to start by subtracting a 2 from both sides. So x minus 2 is equal to 2y squared. Then I'm going to divide by 2. Oh, these guys are stinkers. Okay, I'm going to, I guess, leave it like this for now, equals y squared. And then they took the square root of both sides. So you have the square root of x minus 2 over 2 is equal to y, plus or minus, I suppose. And that's what we have it here. It is x minus 2, and absolutely not a function. 100% no. Okay? All right. Now, last one we're going to do together, number 57. Prove that f of x equals x plus 3 over 2, or prove that if f of x is x plus 3 over 2 and g of x is 2x minus 3, that they are inverses of each other. Okay, remember, to prove that they're inverses, we're going to take f of g of x, and we're going to take g of f of x. Two parts, okay? So for f of g of x, I have x, but this time my x is going to be 2x minus 3 plus 3 over 2. Well, 2x minus 3 plus 3, this is 0. So I have 2x over 2, which equals x. All right? For my g of f of x, I'm going to have 2 times x, but my x is x plus 3 over 2 minus 3. Okay, don't forget these extraneous parts here. These 2's are going to cancel, so I have x plus 3 minus 3 and x. Because they are both equal to x, they are inverses of each other. All right, so that's a simple way to find out if they are inverses. If they didn't both equal x, then they wouldn't be. Yes, they are inverses of each other. Okay? All right, that's it for this section. The next part here is your self-test. As always, if you have any questions or need help with anything extra, please do not hesitate to contact me. Otherwise, until next time.